Welcome to Networks Professionals.
Welcome to The Explainer. Today we're diving into something truly wild, the exact technology that finally allowed machines to, well, literally perceive our world. You know, for the longest time, the digital realm was totally blind, almost entirely text-based or just waiting for us humans to manually feed it structured data. But wow, has that paradigm shifted? Thanks to massive breakthroughs in neural networks, we've actually given the digital world the profound power of sight. So let's jump right in. Seriously, think about it for a second. What actually happens when a machine opens its eyes? For decades, computers were basically blind. Sure, they could crunch crazy complex algorithms in milliseconds, but if you showed them a simple photograph of a crowded street, nothing. They just saw a completely meaningless flat matrix of RGB pixel values, zero semantic understanding of what those pixels actually represented. But today, we're going to unpack exactly how modern algorithms process, categorize, and truly understand that visual reality in real time. It's completely transforming how software interacts with our physical environment.
So here's the crucial paradigm shift. Computer vision, or CV, isn't just like a digital camera snapping a photo. Not at all. It's an artificial brain interpreting spatial data and temporal sequences. It actually equips machines to see and interpret inputs like images and video. And getting to this point, making this huge leap from simply capturing light on a lens to real-time cognition, well, that requires leaning heavily on deep learning models. Specifically, we're talking about convolutional neural networks that parse visual data layer by layer. We've officially moved from just having hardware that records the world to software that actively comprehends it. Okay, here's our roadmap for today. We're going to start with how machines learn to see, and then move on to the 5 vision capabilities. From there, we'll check out the top enterprise vision platforms, dig into open source models and frameworks, and finally wrap up with the future of machine sight. Section 1, the 5 vision capabilities, giving machines visual superpowers. Let's move right into this and examine what happens when we give machines these abilities, breaking down the abstract concept of sight into highly specialized tools. So these 5 core capabilities represent exactly how a machine actively parses human reality. You can think of them as the distinct cognitive functions of the AI's eye. We're talking everything from spotting faces in a crowded room to actually reading the text on a passing bus out in the wild. Each of these models solves a very specific visual problem, and when you combine them, you get a comprehensive, multi-layered understanding of the physical world. Developers essentially stack these super specific capabilities to build complex applications. Think about autonomous vehicles. They have to simultaneously read street signs, avoid pedestrians, and track the exact movement of other cars all in a split second. Let's actually look at the nuances in precision here, because it's super interesting. On one hand, you've got object detection. This identifies an item, let's say a car, and basically just slaps a bounding box around it using simple spatial coordinates. It's computationally fast, making it great for edge devices, and it gives you a general idea of where something is. But contrast that with scene segmentation. This is vastly more precise. It uses pixel-wise classification to strictly define object boundaries. It's not just drawing a box, it's practically coloring inside the lines to map the exact shape, contour, and footprint of that specific car within the environment. Naturally, this is a much heavier computational lift, but it's absolutely crucial for high-stakes tasks, like robotic surgery or autonomous driving, where knowing the exact physical boundary of an object is literally mission-critical. Now, building on that, we see a massive leap in computational complexity the moment we add the dimension of time. Facial recognition is incredible. It maps, verifies, and matches static human features against databases. It's a hugely powerful form of 2D spatial mapping. But action recognition? That actually understands behaviors and movements over time in video sequences. By analyzing optical flow and using 3D convolutions, the system is actively monitoring how pixels change from frame to frame. It's the profound difference between a machine simply knowing who is in the room versus actually understanding what they are doing frame by frame. And finally, we have OCR, or text extraction. This honestly acts as the ultimate bridge. It locates and translates the physical text embedded in our messy, chaotic natural world right into readable, actionable digital data. And doing this in the wild is incredibly tough. I mean, imagine trying to read a warped street sign, or a scribbled menu, or a totally wrinkled t-shirt in low light. The AI actually has to overcome those severe occlusions, extreme lighting variations, and totally unpredictable angles to pull that text right out of the image and turn it into clean, searchable data. Moving on to Section 2, top enterprise vision platforms, the out-of-the-box corporate giants. Let's look at the ecosystem making this tech accessible worldwide.
It is really fascinating to see how the major players have carved out their own specific niches in this landscape. For example, Google Cloud Vision and Amazon Rekognition offer these highly scalable, ready-to-use APIs that require barely any machine learning expertise to deploy. Google is fantastic for foundational face detection and OCR, while Amazon leans heavily into security and event-driven video. Think celebrity recognition or automated content moderation. Then you've got Azure Video Indexer, which ties perfectly into the Microsoft ecosystem for generating deep corporate transcripts and brand identification. But it's not just the big three. We're seeing highly specialized disruptors jumping in. Mixpeak provides these deep full-stack video intelligence pipelines that focus on frame-level visual search. And 12 Labs, they are doing some seriously groundbreaking work with multimodal search using natural language queries. That means you could search a massive video database for a complex action, like a person running while holding a red cup, just by leveraging vector embeddings. No manual human-entered metadata tags required. It is an incredibly robust marketplace right now. Let's pivot slightly for Section 3, Open Source Models and Frameworks, the Tinker's Playground. So this poses a massive question for developers, researchers, and highly specialized businesses. What if you want to build it yourself? What if you want to bypass the corporate APIs entirely and construct this visual brain from scratch? Well, there are plenty of reasons why you might want to. Maybe it's to ensure strict data privacy by keeping everything on your own private air-gapped servers. Or maybe you need to drastically reduce latency for real-time edge computing and manufacturing. Or let's be real, maybe you just want to avoid those hefty recurring API costs. Sometimes building custom solutions is simply the only way forward. If you are going that DIY route, here is your foundational toolkit. These are the absolute pillars. First up, you have YOLO. This stands as the gold standard open source system for lightning-fast, real-time object and face detection. It balances incredible inference speed with high accuracy. Then there's OpenCV, which is your essential, totally battle-tested library for foundational image processing and video streaming tasks. Now, if you need that crazy pixel-level precision we talked about earlier, you've got Meta's SAM-3. This is an advanced segmentation model capable of zero-shot masking. Basically, it can identify and perfectly mask objects it hasn't even been explicitly trained on, using just text or point inputs. Wild, right? And underpinning all of this whole ecosystem are TensorFlow and PyTorch. These are the core heavy-lifting machine learning frameworks that developers use to actually train custom CV models from the ground up. Which brings us to Section 4, the future of machine sight, a world where every lens has a brain. As we wrap up this explainer, we really have to step back and look at the broader implications of having automated content analysis, well, everywhere. Going back to our core definition, remember that this technology isn't just about recording data anymore. A standard camera, it just passively records. But computer vision AI performs active, continuous interpretation. It never gets tired. It's constantly analyzing spatial data and temporal sequences. The machine isn't just watching, it's always interpreting, turning our physical visual world into a continuous stream of structured digital data. And that brings us to the ultimate question. I want to leave you with this final provocative thought today. In a world where every lens essentially has a brain attached, how will human behavior adapt to being truly deeply understood by the machines around us? Seriously, when a camera doesn't just see that you're there, but understands exactly what you're doing and the context of why you're doing it, how does that change the way we move through the world? Thank you so much for joining me on this explainer, and keep your eyes open.
Thanks for watching.